on time with respect for our colleagues that are connected remotely. So, if you want to go ahead.
Okay, so then we will continue the session with a talk by Yongqiang Yu. And please go ahead. I think we don't hear you yet, but
what problem?
Now it's perfect.
Can you hear me?
Yes, we can hear you well.
Okay. Thank you, Chairman. Good afternoon, ladies and gentlemen. Today, on behalf of China Earth Simulator team, I'm going to present an overview about the numerical climate modeling and weather modeling on this simulator. Firstly, I would want to give you a brief introduction to the China Earth System Simulator. Then I show you some examples of the global climate modeling and regional weather and air pollution modeling. And then I show you some support and manage system, and finally, forthcoming plans. Actually, there is a long story of China Earth System Simulator. And this project was first proposed in 2008, about 14 years ago, after some very complex procedures and highly competition with other science proposals. It's formally approved in 2018. The total budget is about 180 million euros. Last year, we established this simulator preliminarily and began trial operation. And 5 months later, about October this year, we will go through the final evaluation by the funding agency. We have 3 key scientific objectives to develop this simulator. First one, to understand and explore mechanisms for the physics, chemistry, biology, process, and their interactions in the Earth system. And the second is to investigate predictability of the Earth system and improve the prediction scale. And the third one is to support the policy development for climate change and natural hazards related to the global warming. This is the overall configuration of the Earth simulator, which integrates the co-designed hardware and the software. We have 5 parts. Firstly is the global Earth system model. The second part is a regional high-precision simulation system, mainly focus on the regional weather extreme events and air pollution. And then the third part is a support and manager system. The fourth one is database data simulation and visualization system. And the fifth part is a supercomputer system. And this simulator was constructed by our Institute of Atmospheric Physics and Tsinghua University. For the global model, we have 7 component model. For example, AGCM, OGCM, aerosol and chemistry model, ocean biogeochemistry model, land biogeochemistry model, land surface model, and dynamic vegetation model. These 7 component model are coupled with coupler. This coupler also developed by Tsinghua University. Besides these 7 components, we also have 3 separate components: solid terrestrial space environment model, ice sheet model, and solid Earth model. These 3 models so far is separate, but in the future years we will couple this separate model with the whole Earth system model. For the regional model, we mainly forecast the numerical simulation and forecast for extreme weather events and air pollution. Left hand shows a high performance computer. And this computer is developed based on high-ground chips. Actually, it's very similar to the early version of AMD, but it's authorized by AMD company, but manufactured in China. And the peak performance is about 15 PF, and the storage is about 80 PB, and 30 PB is online and 50 PB offline. We also have some scientific visualization system, including the virtual reality VR and spherical LED display system. We have a Chinese name of the simulator. This is called Huan. Yeah, this is a new building for the simulator. This is a photo for the computer room. The total budget is about 180 million euro, and began 2018 and this year. Okay, then I want to show some examples for the global climate modeling. Actually, we have developed 2 global models. One is the Earth system model. We call this CAS-ESM, CAS Earth system model. Another is a climate system model, FGOS, flexible global ocean atmosphere land system models. The CAS-ESM has a full carbon cycle, but with cold resolution. The resolution is about 100 kilometers, and FGOS is a climate system model, but with high resolution. And for ECM, the horizontal resolution is about 25 kilometers. For OGCM, it's about 10 kilometers. Both these global models were used for the CMIP-6. We carry out the most CMIP-6 experiments and submit this data to CMIP-6 website. For high-resolution MIP, you can see about 10 models. The highest resolution for ECM is 25 kilometers, and the highest resolution for OGCM is 10 kilometers. FGOS is our model with highest resolution in ocean and in as well as in the atmosphere. Here I want to show some results. This is a simulated carbon cycle by our Earth system model. Red panel shows the CO2 concentration, spatial distribution for January and July. You can find a significant seasonal cycle. It's mainly induced by the land biology processes. Left panel shows the simulated CO2 concentration and the CO2 budget. from observation and model. You can see our model can reproduce the global CO2 concentration since 1850. For the climate system model, this is simulated daily precipitation from 25 kilometer resolution HCM. You can find the large-scale precipitation pattern ITCZ, and also you can find some tropical cyclones. And for example, okay, here is a strong cyclone. We also run model with very high resolution. This is an example. And yeah, we run model with two resolution. One is 10 kilometer, another is 5 kilometer. 5 kilometer in the left panel, in the right panel is from 10 kilometer resolution. This is simulated vorticity. From these two figures, you can find our model can simulate the stronger eddies, but for 10 kilometer OGCM, the scale is much larger than the 5 kilometer resolution OGCM, because in 5 kilometer resolution OGCM, there is some submassive scale eddies, but this submassive scale eddies cannot simulate in the 10 kilometer OGCM. This is simulated EKE and eddy kinetic energy from 5 kilometer OGCM. You can find the very strong EKE along the western boundary current, such as Croatia, in Atlantic along the Gulf Stream, and also in the southern Ocean, you also can find very strong ocean eddies. Okay, I can stop here. Okay, then I want to show you some examples for regional weather and air pollution modeling. For the high precision regional simulation system, this system divided by based WRF model, but we have some modification into WRF model. The regional simulation system was first or nested with a global model or global renaissance. Usually, the typical resolution for global data is about 0.5 degree or 1 degree. Depending on the different purpose, we have different resolution for the region model. For example, for the simulation in the whole China, we use 3 kilometer resolution. But in the East China, we use resolution about 1 kilometer. But for some key cities, such as Beijing and Shanghai, we use the resolution about 50 or 100 meter. Okay. Here I want to show the example for the about 3 months ago. You know, there is a Winter Olympic scheme in February. For this scheme, we developed a 100 meter resolution weather forecast system. Here is Olympic game topography in Olympic game skiing venues. This is a topography. Here is a case study for the rainfall snowfall forecast. in 12th of February. This is a 40-hour precipitation forecast. This forecast is very close to the observational snowfall. Then I want to show the two-way nest simulation. You know, there is a very heavy precipitation in 2012 July in Beijing. In this event, there are about 79 people died due to this heavy precipitation. Here is observed rainfall. You can see very strong precipitation in very short time. But this simulated from global model. The heavy rainfall is weakened and extended long term. This simulation is much smaller, much smoother. Then we use two-way nest regional model to into the global model. We use WRF two-way nesting in our global AGSM. The next one, the lower panel, it is simulation of precipitation in the two-way nest model. You can see the stronger, the heavy precipitation near Beijing is well simulated. Now I want to show an example of air pollution simulation for the PM 2.5, PM 10, dust, and ozone. This case is associated with cold air front system. You can the dust have a long distance transport from North China to South China. It's due to the cold front. Okay. Then I want to show some support and manage system. We have the super simulation support and management systems. These systems have 3 levels. First level is model service, including diagnosis, assessment, and tuning kits. And the second level provides the various physical parameterization schemes and efficient coupler here. And the third level provides the operator library and I/O library, which had the complexities and parallel computing, reduce the difficulty in developing model and promote the model running efficiently. This is an example for the vaccine coronavirus I/O library. When the original version of the ocean model, we call the LICAM, with 1 degree is running with 19,200 CPU cores. Parallel efficient is about 75%. But the half time is used for the I/O. When the vaccine coronavirus I/O library is applied, the I/O time was reduced from 183 per second to the 2 seconds. resulting in overall model acceleration about 1.9 here. And because in this machine, the GPU provides the most computing capability of our simulator. The peak value is about 15 PF. Actually, 2 PF from CPU and the other 13 PF from GPU. So it's very necessary to run model with heterogeneous parallel mode. We have a test for the ocean model. This is a heterogeneous optimization for ocean model LASG with about resolution is 1/10 degree for AMD GPU. Actually, the original model code is Fortune. We transform the Fortune into C, then into heap. Actually, we also try the OpenECC and the CUDA-C, but heap has the most efficient. So this model can run in the heterogeneous parallel model. And this 120 degree ocean model can be run on more than 1 million GPU cores, speed up to 2.7 simulation year per day. It's very high efficient. And this slide, I want to show the visualization system, which includes the virtual reality VR machine and the spherical LED display system. Then they can be used for professional study as well as science popularization and publicity. And finally, I want to show some forthcoming plans. In the future, we will further increase the spatial resolution for global ocean model, maybe 2 or 3 kilometers, for global atmosphere model, about 5 to 10 kilometers. Then we continue to improve the Earth system model. In particular, we want to introduce new component model, such as ice sheet model and solid terrestrial environment model. Then we want to develop a coupled data system, data simulation system, and climate prediction system. Finally, here I want to emphasize here, both computer and software, including model and the supporting system, will be open to all scientists over the world. So everybody is welcome to use our simulator. That's all. Thank you.
Okay, so there are no online questions in the Google Docs. Do we have any questions to you here in the audience? From the modeling specialists? Yeah, Sylvie. So I hope the speaker can hear us.
Yes, thank you very much for this very interesting talk. I would like to ask you on the two aspects. On first, maybe on the computer. I'm not sure you say much about the computer itself. What are its characteristics? And second, after 2022, what are the when you say there is an evaluation in 2022 that's deciding the next phase of the budget, or what are the ideas after 2022?
Sorry. Sorry. Can you repeat your question?
Okay, so I try again, sorry. So do you hear me?
Yes.
Okay, so two parts of the question. First, on the HPC system itself you are using, you said it has been co-designed. If you can tell us a bit more on this. And second, on what are the plans after this evaluation in 2022? So the ambitions for the overall system, not just in terms of resolution, but also in terms of computer aspects.
What's the first question?
Maybe we can do so that if you write the question in the chat, and if you can answer in the chat, then we anyway are a bit out of time already, so maybe we move on to the next presentation now. But so if you Yongqiang, if you can answer to the question in the Google document where you got the link.
Oh, okay.
That's great.
The setting is not too good. I can answer question in the Google document.
That's
Thank
great.
you.
That's perfect.
Great.
Thank you very
So
much.
thanks. Yeah, thanks again. So, and now I think our technical guys will magically switch over to Nils from ECMWF, who's probably sitting somewhere in Scandinavia right now.
Okay, can you see that?
Yeah, hi Nils, we can see you.
Okay,
And we can hear you.
Joachim. Thank you for the introduction, and yeah, really apologies that I can't be in Barcelona. So I'm heading for a more northerly kind of shores, and there was a bit of a clash. So unfortunately, I can't meet you in person. But yeah, so basically, I wanted to talk about opportunities and challenges for the digital twins of the Earth system as part of the Destination Earth initiative. And I'd like to basically introduce to you both the concept of digital twins and this initiative funded by the European Union. So we all know these pictures and comparisons of the observed Earth system versus the simulated Earth system on the right-hand side. What we do today operationally with the IFS model that has already been introduced by other speakers like Sam. And when we increase the resolution, even though we're still having to work on the color scaling of the actual radiation fluxes, we do see basically an increase in realism and quite a match for the often advocated Turing test. What is real and what is actually the simulated environment. And this inspires us. But of course, with digital twins, we want to go beyond this. And we want to be basically much more interactive with our Earth and the climate system. And the idea of digital twins is not new. It's something that's been explored in a number of other disciplines. And it is really trying to capitalize on the advances in digital technology and bringing together the agenda of understanding and managing climate change with the agenda of a digital strategy moving forward into the next years. So it is much more than just a data mapping exercise, and this is something that I would like to illustrate in the next few slides. So this is also something that a number of market players have invested in and are continuing to invest in, like NVIDIA here. And it's really for them also these new horizons of machine learning, autonomous driving, and gaming engines actually that are blurring really the real and the physical world. And it is also trying to capitalize on these advances. And further to this, really, a lot of people say, okay, I want my own digital twin in order to really map between the physical world and the digital world. But you can start to see many other different attributes that people associate with the word digital twin. That also gives basically aspects of this fascination of what a digital twin is. But for us, in Destination Earth, it is also a challenge with respect to managing these different perceptions, what really we want to achieve from this digital twin. And I just listed here many different keywords that I have now and in recent times heard at various conferences and so on. And I think there's a story behind many of these, and you probably will have another set of words that come to your mind when you think about bridging the physical world into the digital world and thinking about a digital twin. But many of these words are really important, and it's something that much of it we want to achieve basically in Destination Earth, but much of it we also will be challenged by. And if you have any particular question to any of these keywords, then please ask me afterwards. So I mentioned before, technology is really one of the aspects, of course, one of the driving aspects why we can perhaps move forward in this and why we can try and push the envelope, as we have always done actually in weather and climate modeling over the past 40 years. So the aspect of adaptation to the computing architectures is one aspect, but also the emerging elements of cloud technologies, democratizing the existence of HPC resources in different countries, the access using cloud systems of a variety of federated or distributed data sources is something that is coming together, if you like, in this Destination Earth initiative. So on a political level, this is really addressing the European Green Deal on the one side and the Europe's digital strategy on the other. It is implemented by, so it's funded by the European Union, but it's implemented by 3 entities. This is ECMWF, responsible for the digital twins, the 2 first digital twins for extremes and climate change adaptation, but also then the aspects of climate, of workflows, HPC workflows, and the digital twin engine concept that I will come to in a minute. Then there's ESA implementing the core service platform with respect to the interface to the users, the interface for user registration, also delivering cloud space for managing data access, managing information flow, and also being able to actually employ, if you like, your own applications operating on the data. So there will be user space readily available. And then the data lake, of course, which is handling much of the information flow on the data side from the digital twins, from the HPC, all the way to the individual users accessing the core service platform. So I mentioned already EuroHPC. You had a talk from Lumi, and this is also, of course, a great, one of the big contributions of EuroHPC. So I'm coming to that in a minute as well. So for ECMWF's role, it is, as I said, implementing this digital twin engine that facilitates much of the implementation of digital twins and helps to operate them, helps to monitoring them, helps to contribute to an efficient and optimized data flow from the digital twin to the data lake. We have these 2 priority digital twins. And also we will look at different use cases that both illustrate the system, but also how we can maybe visualize and use some of these immersive technologies that I mentioned before. So it's in 2 phases. The first phase is from 2021 to 2024. And hopefully the second phase will be from 24 with yet undefined, I think, end date, but probably like 27, 28. And so some of these capabilities will have to be delivered fairly soon. So there's quite some time pressure in terms of delivering a first shot at blurring the physical world and the digital world. So I mentioned this digital twin engine, which is something that ECMWF is working on. So it's really a common system approach to a unified orchestration of Earth system simulations and also this fusion of observations with modeling. So on the one side, it's about controlling digital twins and the interaction with the core service platform. And on the other side, it's actually running these digital twins and contributing to this data production, the processing of the data, and access to tools and interfaces. And so really, this is representing ECMWF's 40+ years of experience in HPC and in delivery of time-critical weather and climate monitoring information. So then I mentioned EuroHPC, which is, of course, the resource that we're going to use in DestinE in order to deliver some of these ambitious goals. This Looming system was already mentioned, but you can see here also, let's move this a little bit to the side. So you'd see Mare Nostrum, which is about to be, I think, announced, and then also Leonardo in Italy. These are the three big systems, but there are a range of smaller systems as well, of the size of Archer in the UK. And in fact, there are procurements ongoing at the moment for 1 to 2 high-end supercomputers of an exaflop by 23-24. So these will be the systems that will be running some of these digital twins. And then it is up to us basically to manage this interaction. So one of the aspects that is also important is that this is do you see these as well? These okay.
Yes, we see it.
Right. There we go. That's easier. So what you see basically here is also that the current proposal from the governing board of the EuroHPC is to set aside a maximum of about 10% of the union's access for strategic initiatives on these machines. And this is precisely what DestinE is, and this is helping with the delivery of the DestinE goals. So, of course, this was already mentioned by some of the other talks. Efficiency and accuracy advances in these different directions, both on the technology side as well as on the science side, will be elements of DestinE delivery as well. Code portability, and especially the aspect of the GPU and the use of both CPU and GPU on these hybrid systems that all of the EuroHPC machines really provide, is going to be, of course, one of the challenges for these digital twins. So then the other functionality that I mentioned was the data lake that is procured by EUMETSAT. So this is really about a self-standing component built from geographically distributed physical elements that references and provides seamless access to DestinE user-required data. So this is both on the input side, perhaps for DestinE digital twins, but also, of course, on the output side. So handling the actual digital twin data to provide this to the users and of course, part of this process will be also a major reduction of information from the digital twins, producing at very high volume data rates towards something that can be transmitted over the, the least, say, strong lines. Even though EuroHPC will be connected to JAND at a very reasonable speed of, say, 100 gigabits a second, there will be slower lines, of course, as you go towards the user ends, and that needs to be thought about in a scalable way. Another aspect is also the idea from EUMETSAT to provide harmonization of data access, because there's, of course, all these other data sources like the satellite data, the Sentinels from EUMETSAT and ESA, with different data portfolios contributing to DestinE. And then I mentioned as well the core service platform, which is the element of the portal to the user, as I said before, a My DestinE workspace for users, cataloging of data, and the provision of a platform as a service, as well as software as a service for analytics and modeling, machine learning in particular, where data spaces and compute spaces are going to be made available to the user side. So this is just a draft of the digital twin engine interface, say, as a reference architecture to the data lake. So you see here split the responsibility of ECMWF in pink and the responsibility of EUMETSAT on the right in green, and you see that we also are executing elements on the EUMETSAT infrastructure in order to optimize data access flow from the EuroHPC machines to the infrastructure that EUMETSAT is going to procure. So there has to be also a close dialogue, of course, with the EuroHPC sites in order to facilitate some of this, because we are talking really of hardware that EUMETSAT is procuring, with ECMWF is very much contributing software solutions that will use some of the infrastructure as a service provision given by EUMETSAT. But this is sort of the dialogues that we have at the moment between the three entities in order to define these interfaces. And this will then facilitate these workflows that I mentioned, from high-performance computing and cloud computing on the one end to big data handling across, also bringing the compute to the data as much as possible, and the user interface at the other end as well, in order to receive the results and actively interact also with digital twins that I didn't talk much about yet, but there's a lot going on as well in order to facilitate really interaction with the digital twins and make of some of this dream at least feasible, where there can be influence on the simulations themselves. So we anticipate therefore production modes that both continuous on the one side, as well as also workflows that are on demand. So they could be user-driven, they could be event-driven, they could be periodic, they could be also just addressing particular needs or reruns of reproducing data that may have been not stored, and where for specific applications you may need something very special. Now, just as we reacted, say, to the pandemic, we may be reacting to climate emergencies in a similar way. And then, of course, I mentioned machine learning here, just a range of ideas that will help in the process of setting up these digital twins. I won't read them out all in detail, but it's really about speeding them up, improving them, building new tools, and enabling new science. And there is a lot of research, of course, ongoing as well at the moment, where, in fact, we may really think about how we model perhaps elements in the future. And there will definitely be an interaction between, say, the physical modeling on the one side and the emulation machine learning type modeling, and emulating particular parts, including parts of the equations in the future. And then, of course, there's the uptake with respect to the different sectors like health, energy, transport, pollution, and extremes that we would like to target, and where machine learning can clearly help. Because it is, after all, a new tool that allows perhaps a more systematic way of interacting really with the user side, from expert information on the one hand to, say, the user on the other, or the policy on the other side. So we are not the only game in town. There are a lot of other digital twins emerging. Like one example here is the digital twins of the ocean, and there's not only one digital twin of the ocean. There's a Mercator-driven initiative. There is also this global program of the UN, Decade of Ocean for Sustainable Development, DITO. And then there's also Horizon Europe, R&I project, Iliad, which has recently been funded and starting up. And they're all looking at how we can interact. And one of the aspects that is really important going forward into the future is how interoperability can be facilitated, what kind of standards we're using, and how we can actually work together. So we have this partnership program in Destination Earth, where we emphasize on some of the aspects of interoperability on the software infrastructures, in particular for Destination Earth. For us, the importance is this digital twin engine, which represents, in fact, some of these standards and ideas that, of course, was a heritage from numerical weather prediction. But the numerical weather prediction heritage is not something bad. It's something where, it brings in the experience of really operationalizing certain workflows, and that's something that we would like to bring to this initiative. And of course, then when new destinations like digital twins are coming for phase 2, where you want to incorporate others, one could think of like a full integration mode, or like a coupling mode, or maybe just a post-processing mode. And it depends very much whether the interactions are really on the modeling side as well, or whether they are more on the data-driven side, or in what other kind of innovative ways we are thinking of integrating and interoperating with a range, say, of digital twins in the future. So there's all these partnerships also for creating synergies across different programs. So we have, of course, the Destination Earth, digital twins, platforms, and Lake on the one corner. In this kite, but we have the services, of course, with Copernicus, environment agencies, and so on, the member states. On the other side, we have, of course, all the science aspect of Earth system and impact science as well. And then this technology infrastructure. So I mentioned the Euro HPC, but there is more. There's a European Open Science Cloud. There's other initiatives in order to bring together more interconnected, both HPC and cloud systems to a wider audience and use it basically for a common purpose that allows data fusion across different domains. And that, I think, something that, is a big vision, and in the detail it's going to be complicated, but we're really trying to achieve a contribution in Destination Earth. And that's it for me. So if you have any further information, it will be on the website here, and if you have any questions, then feel free to get in touch.
Thank you very much for the interesting talk. So we have some questions here in the Google Doc. So the first question is by JC Andre. Do you already have started to work with some future users of the digital twins?
We haven't, because currently we're in the process of evaluating the responses we have received to some of these procurements. They will have some user interactions involved. We are developing at the moment a partnership plan together with the 3 entities and also with the Commission. And we also are preparing at the moment a procurement for use cases where people can in fact respond to our procurement and propose a use case where they also have to define, say, the readiness for using, say, the data that we are going to provide and the data that is out there, and how their vision basically is in interacting with a Destination Earth-like system. So this ITT will be published. I don't know the exact publishing date, but I think it's going to be in a month or so.
Okay, thank you very much. Then there are more questions. So then there's a question by Kim, but maybe I will read it. So which are the major HPC challenges of Destination Earth program?
Well, there will be challenges for sure with respect to adaptation, but we hope that the models are reasonably ready to actually make effective use. So we are, reasonably advanced for that one. There will be challenges with respect to the very large data flows that I mentioned. So there was some innovation required in order to for the data reduction, if you like. There will also be challenges with respect to managing these very large data flows, because we are talking about kilometer scale models with very unprecedented data amounts running routinely on these machines. So we have to very actively look at our data management policy. What do you want to keep in terms of, and what do you really want to extract from the information? Of course, the ultimate dream would be if you could have, if you could learn the data and just kind of, have a machine learning algorithm that basically designs, if you like, a system that replaces storing with extracting the key information and into an algorithm that can reproduce it when you need it. But I think we won't be ready with that in the next 2 years for sure. So I think we certainly will evolve, but I think there need to be innovative ways of dealing with these huge amounts of information and how we can fuse this information in a sometimes time critical fashion.
Okay, thank you. Okay, then one more question by Brian. Is the partnership going to be allowed to extend to non-EC partners, at least in terms of collaboration?
Yes, obviously on a non-funded basis, yeah, absolutely. Now, as you know, there is politics involved with respect to funded collaborations. But we have reached out already as part of the Digital Twin Oceans. I just attended an event in the UK, actually, where there's a number of initiatives going in similar directions. And we're very open and very keen to understand the needs and also setting up say, our system in such a way that maybe at the future time, this would allow incorporation of initiatives that currently cannot be funded under the Commission.
Okay, thank you very much. Yes, so let's thank Nils again. And then we can move on to the final talk of the session. So that will be given by Jean-François Lamarque from NCAR.
Yes. And can you see this? Can you see my slides?
Yes, we can see you. We don't yet see your slides. But we hear you, and I think you can continue. Yes.
Okay. But if you don't see my slides, then it's not.
Yeah, but the streaming. Yeah.
You can see my slides. Okay. Okay. Great. So thank you for inviting me to give this presentation. And so this will be maybe somewhat similar to the presentation from Nils earlier, right before me, kind of high level on where we're going here with CMIP. So just because I'm not sure how many people are familiar here with CMIP. CMIP is the coupled model intercomparison project. I'm the current chair right now, but what the main objective of excuse me, of CMIP is to understand past, present, and future climate change from natural or in response to changes in greenhouse gases, aerosols, in a multi-model context. So that's a very key aspect to CMIP, is that we really strive for a multi-model approach to doing the science and understanding climate change. Started in '95, has a very tried to strive for a very well-defined set of experiments. Some are very idealized, like the 1% CO2 increase from pre-industrial to 2x, 4x, that sort of things. And started with just a few models about almost 30 years ago now. And we've seen an exponential growth in the number of participants and the overall size of the project as well. One thing that is key, I believe, to CMIP is that there's a dual role that we're trying to achieve here. One is really a scientific enterprise. This is driven by scientific questions on understanding and narrowing down uncertainties about climate change, potential tipping points, all sorts of things that are related to what the future can hold. And also a very well-defined support for policymakers. So we're trying to get those two items, and I think that's one of the critical tensions to what CMIP does and how it does it. We've played a really, I've seen, as you probably know, that CMIP has been playing a really critical role in supporting IPCC assessment reports and many other reports, in addition to driving the science through many of the papers that are written out of the CMIP. Interestingly enough, this, or maybe not, this is actually a fairly extensive cost associated with that. Although one has to be careful here. It's not just CMIP here that would be that should be considered under this cost, but it's really the overall climate modeling enterprise of building models, running models, testing the models, and all that over a cycle of many years. And so people, this is WCRP, World Climate Research Program, sorry for the acronyms, report that people try to estimate that as being 3 billion. And so whatever the number is, this is a very, it's a lot of investment that is being put really worldwide. And so it's a very distributed environment that we're dealing with. So CMIP 6, in and of itself, had a participation of about 110 different models, model versions, coming up from 44, 50, depends how active some of the groups were, but let's say about 45 modeling centers around the globe. And one thing that we have seen over time is the growth from being from United States, Europe, to many other countries now are really trying to develop their own capability and knowledge of climate modeling or system modeling. So we have this participation to CMIP as being the deck, which is kind of the core set of looking at some of the most fundamental performance of the model using a pre-industrial control, so constant 1850 conditions, run for a long time. The 1% CO2 I mentioned before, the instantaneous 4x CO2, and those are what is being used for the very standard measures that you probably heard of, like the climate sensitivity, the transient climate response. So those are very useful metrics, and so those are the based on what we call the deck. And then the MIPS, which are very much driven by scientific questions. What would be the response of the system to aerosols? I was involved in AirCam, right? So there is this very complex set of simulations that we call MIPS. And then what comes out of it is some of those really iconic simulations and iconic results. This is just one of them. And in a way, I'm doing a disservice here because I think the strength of CMIP, and especially CMIP 5, CMIP 6 more recently, is really to dig into the full understanding of the Earth system way beyond just a global temperature. But this is still one of the iconic questions and graphs that people like to relate to in terms of the IPCC understanding of the Earth system. CMIP 6 is generating what I would consider a very large amount of data. And so right now, for all the simulations in the span of about 3-4 years, there's about 11 petabyte that is being now distributed by the Earth System Grid Federation. And I'd like to thank Paul Dirac from Lawrence Livermore for this figure. So this is the basis for the distribution of all the simulations from all the models in a common format, so that people can dig into that and answer their questions using those simulations. And it's, to me, that's how we actually get the information that we want out of those models. It's through the distribution. It's that after the definition of what are the science questions, how we can address it, how the models are going to run those simulations. They run the simulations and then the data. How are we actually going to now analyze the data and get people the answers that they want? Interestingly enough, this is not something that we've been wondering about, is how we're going to deal with all this data. And what Nils was just mentioning earlier, I really like the analogy of a data lake. This is not a data pond anymore. This is a data lake, and I think we're getting close to the data ocean at this point. Is how we're going to actually analyze those petabytes and whether those projections are realistic or not. I think they might be underestimating the progression that we will see over the next few years or decade on how we're going to look at this data. One thing that we're trying right now is, so CMIP 6 basically ended or is still in some state of evolution, but we're starting to think of the next phases of CMIP. And so we submitted a survey earlier this year, and we're looking into the analysis of this data. I've been fairly pleased that we've been getting respondents to the survey from a variety of groups, obviously mostly a good chunk from Europe, which really identifies, in my mind, is really representing now the core of the activities. for the climate modeling and Earth system modeling, but also some of the other countries, and Asia is starting to play a big role here. And we are seeing a combination of people who are responding, and the majority of the people are responding in terms of the CMIP output analysis. And I think, again, that's the reflection of how we are actually reaching to other people to what they want to do. So we're trying to understand what was working and what was not working under CMIP-6, and this is going to be part of the conversation. There's going to be a conversation with the broader community of modelers in particular, because without the modeling groups, and there is no CMIP. And so we're trying to understand some of those MIPs, which ones were the most interesting or the most used. And again, is this for science or is it for policymaking? The overall sense that I get from the analysis of the survey so far is that the scientific focus of CMIP-6, people were quite satisfied. So I think we're moving into the future, we're probably not going to change completely radically the way we do things. We might adjust. There have been other things, COVID, one of them, and then maybe there's understanding the climate sensitivity, those very high climate sensitivity models. So there are approaches, and so I think we need to revise some of this distribution here of MIPS on what is the most interesting science that we want to do over the next few years. So some of the key points here is that I think there is an overall support for the overall scientific focus, and it's a large investment. So I think one key here, and that's what I'm going to go a little further in the rest of my presentation, is how do we optimize the HPC resources? And I mean this in the broad sense of not just HPC as running the model, but also the data analysis. And in that sense, one key aspect, I believe, is to maximize the relevance of the simulations and of the generated data. And that should be to really support the broad array of people that we're trying to support with CMIP. And this is, in particular, this is a figure that was done a few years ago, and I couldn't remember how I made this figure, so I couldn't update it. But the download, and this is rough, right? But the download volume of data by continent is really just too much in the north. There is not enough of the capability in the south to really analyze the data. And I think, again, going back to what Nils was showing, I think that type of approach where there is the availability for users to really dig into the data without having to bring it where they are is going to be key. So I think there is another aspect, if this is not complicated enough. I think we have, as climate scientists, we have to be recognizing the fact that there is a very significant carbon footprint that is associated with all those computations that are being made. And the world is moving into strong mitigation that is needed, 50% by 2030, or whatever the numbers really are. And so I think it is not going to be justifiable to ignore this fact much longer. Yes, the computers are becoming more efficient, but I don't think they're getting more efficient fast enough to really reach those goals of 50% reduction. If we feel this is, as a community, this is something that we should strive for. So I think we're going to have to be really careful about monitoring the carbon footprint. That should be part of the definition of what we're going to do. We're going to have to optimize also the carbon footprint from both the computing, the data center, energy supplier, use that energy wisely. And this is something, and I think the author will be presenting an update of this tomorrow morning, so hopefully I'm not stealing his fire here. But the models are using a tremendous amount of energy to perform those simulations. I mean, I think that for CESM, which I was part of the development team, we probably did about 25,000 years of simulations to get the model ready and do all the simulations. So this is an enormous investment, and that was at a fairly coarse resolution of 1 degree. We're probably going to go to higher resolution. So if nothing else, this cost is expecting to balloon even more. And then, and this is something that I'm sure the people in the audience, and by the way, I'm really sorry I couldn't join. It would be great. Plus, I love Barcelona. Data storage is an enormous carbon footprint. So I think we have to be really careful. 11 petabytes is a very significant amount, and we're probably looking at much significant increases over this size. So moving forward, what I really think is, like, can we start really thinking about reducing the CMIP 7 emissions over what we did? And as part of this is, how much can we reuse? Do we really need, how many MIPS, how many scenarios do we really need? How many ensembles do we really need? So I think there is science that needs to be done to get a full understanding, to answer the questions that we want to answer, because we still have to answer the questions that should still be the main driver. But what is the optimal set of configurations that we will need? What is the advantage? What is the added value of having high resolution? And so basically, can we optimize data storage and analysis? Lossy compression, we've been looking into this. This would be easily reducing by several factors the amount of data that is being stored. But more generally, what I'm looking for into the definition of the next phases of CMIP is to get a better and more efficient way to get organized. And this will be only achieved, in my opinion, if if we want to achieve all the CMIP objectives, which I really want to emphasize, they're both societal and scientific relevance. And we cannot ignore at this point the carbon footprint, especially for a climate group. It's too easy to be targeted as not being careful about what we do and how we do it. And the final driver is accessibility to the data, so that people in their countries, with the knowledge that they have of what is happening in the ground, can do the analysis, can interrogate the data the way they need to answer the question they need at the regional and possibly even local aspects, if it's relevant. And then what is clear to me is that the group that is being represented here and all the other parties, and it's only if we work together, if we from the scientists interested in doing some of the simulations, we have a full understanding of what can be done in terms of computational power, but also use of power and data storage. So it's really all the expertise that you guys are representing right now in the room, working with the leadership of CMIP. It's only if we do that we will be able to achieve those. So this is basically a heads up. I will be reaching out over the next few months as we start putting all the next phase of CMIP. I will be reaching out to really get all the parties involved and around the table. And with that, I welcome any questions.
There are already some questions in Google Docs. So first by JC Andre. I'm a bit surprised by the 11 petabytes of CMIP data you mentioned in one of your slides. For the only European models, we have estimated that 8 petabytes of CMIP data have been transferred to ESGF, or are we speaking of different data?
So this is the published data. So that's the data that is being published on the ESGF. If there is a discrepancy, then I would send the information to Paul Dirac. But that's my understanding. That's the current, as of last week, the current holdings of what ESGF has under the CMIP6 distribution.
Yeah, Jean-François, if I can add to that, this is Balaji. It's 11 petabytes of unique data, which is the current number, and that's also the correct number. So CMCC has a tool that is monitoring the holdings every hour, including replicas on ESGF. The total is somewhere about 20.
Okay, thank you.
So I don't know whether Jean-Claude's number includes multiple copies of the same data or just one copy. So.
Sorry. Also about this, I think that in the Jaclon presentation, we will provide more information about the specific data, which specific data was published, and also split this specific useful data in exactly what is the most important which was published in the ESDF. So more information about this tomorrow. We were working on this.
Thank you.
Okay, great. Then there was some discussion in the Google Docs, but maybe we can skip as there was already some answers to the next question. So then there was question by Suvi, are the results of the survey somewhere? And then the second question is that, are there any plans to change the way the data is disseminated? I'm wondering on ways to reduce data transfer or download and make it efficient to analyze data. One example could be if ESGF nodes can have some compute resources to do commonly done operations like regridding some derived variables and so on, and this can be cached for subsequent users.
All right. So those are great questions. The survey results are not public yet. We haven't fully. We closed it, I think, a few weeks ago. So the results are going to be published in a journal at some point. Probably we're targeting summer, maybe fall, most likely fall, as a summary. I don't know if we will ever publish the actual data. That's a really good question. I'll make sure that I'm not breaking any rule of privacy and of disseminating the data. So, but yes. So we're starting. So as you probably know, there is a project office that just started, a CMIP project office. So we just started. So we're getting all the people involved, and but so it's going to take a few months to look at all the data. In terms of yes, I think, and there has been some of those. I believe DKRZ and some of the UK groups have attached to their ESGF nodes, or at least have a local set of disks that can be used for analysis. I think it is, to my understanding, that is still it's not open to the public, so it's not like anyone can do that. It's open to collaborators, and there might be limits on the collaborators, but in my mind, yes, that is the way we can and we will be able to increase the accessibility of the data. And there is no way, and I've had discussions with great people from South Africa in particular, and they just don't have the bandwidth to download the data. So either they have access to some repository of CMIP6 data that, like there's one set of data that's available on Amazon Web Services, and there are also all sorts of issues with that, because there was just a snapshot of what was available on the System Grid Federation at that point, so it's not updated. There might be errors there that they didn't catch, so it's a little tricky. It's far from perfect, but it is enabling the scientists to do some of the analysis that they wouldn't be able otherwise. So yes, I think, and this is where I will need, clearly it's not my area of expertise, so this is where I will need people around this room to help the whole enterprise define how we can move forward and generate the information and the solution, because that's what we're after. It's a great question.
Thank you. Yeah, there was also some discussion on the CO2 emissions, but there was already some answers and so on. So everyone can have a look at the Google Docs if you want to see the discussion. But then I think if there are no more questions, then we can thank you once more. So thank you. And then we can close this session and we will have a coffee break of half an hour.
Yeah, so we have half an hour. There are cookies, coffees and fruits there. And my recommendation is to take, and if you go to the terrace, it would be nice. Thank you.
Ist auch keine Lösung, aber